Thanks everyone for joining us for this webinar, which we're holding today to commemorate the 50-year anniversary of the Lonely Halls meeting, which we're using to mark 50 years of GPS. John, our speaker, will go into a little bit more detail about why we're using that date. So let me just quickly introduce our speakers today. Our main speaker is John Owen. John ran the UK GPS programme from 1990 through to 2010. Joining John today are representatives to the GPS JPO and NATO teams, Snowball, Lyn Dutton, John Stevenson and Tony Anderson, as well as members of the navigation team in the RAE and the MOD, Roger Stokes and Rob Linham. There's some great photos of them from their younger days as well, so keep an eye out for those as they come up. So the webinar today will be exploring the development of GPS through ongoing engagement between the US and UK over the last 50 years. And just some housekeeping before I hand over to the interesting part of this. So the recording is happening as we speak. It will go on the Virtual Museum website. Just move on the slide, please, John. Yeah, so it'll be going on the Virtual Museum website, which is available under the resource tab on the website. And this is also one of the first events for the Navigation Heritage Special Interest Group. If you're interested in hearing more about that or getting involved, please shoot me an email at pam.sherrod@ren.org.uk. So there will also be opportunities for questions at the end. If you come up with a question during the presentation, please do drop it in the Q&A section just at the bottom of the webinar screen. And we'll get through as many as we can. I'm sure there's going to be tons. It's such an interesting webinar today. So without further ado, I'll hand over to John Pottle, rather than Owen, to give us a little bit of an introduction. Thank you.
Yeah, hello everybody. As you saw by me just running across the room there, we're actually in the same room, even though the background here looks completely different to over there. So we're in the RIN conference room in London. And as you may be aware, there are a number of events going on in the US to mark the fact that it's 50 years since the so-called Lonely Halls meeting, when the GPS and other now GNSS global navigation system parameters were kind of decided, the trade-offs were worked out. John will talk much more about those, but this is our recognition in the RIN that there was a lot of collaboration between the UK and the US. And I've seen a bit of a run through of what you're about to see, and I thought I knew a little bit about this, and I realized that that's exactly right. I only knew a little bit. There's an absolute host of information that you're about to hear. So I'll hand over now to John Owen and the team. Please take it away.
Good afternoon, everyone. Welcome. I have beside me some of the members of the NATO team and some people from UK who used to be in UK industry and in the Ministry of Defence. Right. This is as Hannah's introduction, a review of the 50 years of GPS and basically how UK became involved in the programme. First of all, a bit about me. I joined the Royal Aircraft Establishment on the 4th of December 1974, and I worked for a Tom Blackman. Tom was well known in the radio world, and he'd actually set up one of the chain home stations at Kingston Wood under Robert Watson Watt, who was a founder member of the RIN. In those days, RE was an exciting place to work because we had these to play with. That's a converted Comet 4 airliner, and it looks a bit like a Nimrod, and we were doing various communication trials to try and improve Nimrod's communication. Other things that were going on in materials department, they had just invented the way of manufacturing carbon fibre, although carbon fibre had been known for about 100 years. How to make it was a big problem that they solved. Down the other end of the airfield, there was the Concorde fatigued test rig. Fred Jones was in the accident investigation department, and Dr. King Healy, FRS, was doing great things with orbit determinations in Space Department. One of the things that came out of Space Department was a way of describing orbits that could cover the Earth. So the Walker pattern, and Walker patterns are used to describe the GPS orbits and the Galileo orbits. And it defines the angle of inclination, the total number of satellites, the number of planes the satellites are divided into, and the relative phasing between those satellites in each plane. So GPS is a nominal Walker, 24 satellites in 3 planes, spaced out 1 satellite phasing per plane. The situation in RE was interesting because Frank Travail, who was the RE secretary, made a very interesting comment on some of the geniuses that were present in the organization. Early developments of satellite and navigation. The first of the systems was transit. Transit was developed by 2 physicists in the Applied Physics Lab in the US from observation of Sputnik data. And what they realized was they were trying to determine the Sputnik's orbit, the position of the satellite in orbit. But they then realized that if they could detect the Doppler shift from the satellite and they knew where the satellite was, they could determine their location on Earth. And that's how transit became a system. It was first launched by the US Navy in 1959. However, transit had a problem that because you had to look at the signal for a significant length of time, the accuracy degraded by approximately 100 meters for every 4 knots you traveled, or every 1 kilometer. So it was a system okay for maritime use where it was where your velocity was fairly slow. It wasn't very good for systems where you had a high velocity, i.e. aircraft. And then Magnavox and Dr. Charlie Kahn got in on the act of looking at how to develop future systems. And his work into spread spectrum signal processing in the 1960s led to the development of the US Air Force Project 621B. He did give, if you can find this in the literature, a very good AGARD NATO lecture series in 1973. It's almost the work of art. And that led to Magnavox developing with the Aerospace Corporation, the 621B program, using high quality accuracy clocks. Their prototype system was actually tethered in balloons at White Sands Air Force Base from 68 to 71, but the results were not outstanding. A receiver was built by Dr. Lenny Jacobson in the Magnavox research labs, and that did improve things a little, but there were still problems. The US Navy were going down a completely different route with their Timation satellites from 1964 onwards. Timation proved a system using passive ranging combined with high performance crystal oscillator clocks could provide the basis for good satellite navigation, and that they achieved reasonable 4-dimensional capability. But we come to where GPS started. You can find on YouTube a very interesting conversation with Dr. Brad Parkinson, where he tells that he was directed by his boss to go and sort out this mismatch between transit, timation, and Project 621B, and to create navigation by satellite time and ranging, which was Navstar, or which has become known as GPS. The problem, he convened a meeting in the Pentagon, as Hannah was saying, in Labor Day of 1973, termed the Lonely Holes meeting, where the problem was resolved, and the DoD put in funding 2 months later in December 73 to start the program. Note, it was to be a military-only system with encryption. So the accuracy was degraded by an encryption process to about 100 meters, and the signals in white code was encrypted to prevent unauthorized acquisition. However, we were fortunate because the cryptography took them many years to develop, and so wasn't activated in the early 1990s. So the initial developments, we have 621B, timation, and then we get to GPS phase 0, and then followed, as we will see, by GPS phase 1 and phase 2 programs. Where UK came in was a visit to the JPO in June 76, so we were in pretty early, about 18 months after the start of the full GPS program. The requirements for instant time and position was an interesting concept, because that was difficult and took some satellite development to do so. The Naval Research Labs had their timation satellites, NTS-1, launched in 1974, and that was followed by NTS-2 in June 77. NTS-2 was noted that it was the first time that cesium frequency standards had been flown in space. And that was the key to the problem, or the key to resolving one of the problems. It was also one of the first examples of a satellite experiment that verified Einstein's relativistic clock shifts. And that work was done by Paul Johnson in aerospace. So UK's participation was kicked off by RN2, division leader Nigel Hughes. RN2 looked after the whole range of radio navigation aids, from ILS down to Omega, DME, Loran's, all the civil navigation systems. The Advanced Systems Group was established in late 1975, headed by Graham Cook, who transferred from Space Department specifically to run the program. I was in the antennas research group at RE, and we were transferred into from RN4 into RN2, specifically to look after the antenna systems, including a anti-jamming adaptive array system. Note, we recognized GPS vulnerability to interference and jamming from a very early start. A team from RE visited the GPS Joint Program Office in June of 1976 and had a long conversation with Paul Johansen from the Aerospace Corporation, and were provided with a whole host of documents about the system. The US were very keen to get us involved. At that stage, there were 3 phases planned: a phase 1, 74 to 78, with 6 experimental satellites, then a phase 2, which began to fill in the constellation with 9 more satellites, and then the full development phase from 81 to 85, where 24 satellites would be launched with complete Earth coverage. At that stage, it was planned to launch the satellites by this space shuttle. Unfortunately, the Challenger accident of the shuttle meant that the satellite had to be re-engineered for rocket launch, which was a big change in the program. And Lyn Dutton will say a bit more about that later. That visit led to a bilateral between the UK and the US for the development of our participation in the system. An important outcome of that bilateral was that UK hosted one of the NTS-2 ground stations, which gave us access to the collected data that was used by the Space Department in their work for orbit determination. The ground station was based at then the UK Royal Greenwich Observatory at Hurstmonceux in Sussex. The other stations were at Chesapeake Bay, UK Naval Station Panama, and the NASA tracking station in Australia. Hurstmonceux is now part of the Global Geodetic Observations System and laser rangefinding. The NATO steering group and team, we were encouraging the US to get NATO involved, and that began to happen in 1978. I'll hand over to Lyn for the next part of the presentation.
Thank you. Good afternoon, everybody. I was a member of the GPS NATO team out in El Segundo in Los Angeles from 1984 through 1987. And I was a Royal Air Force officer at the time, having just come fresh out of 5 years flight test at Bottom Down. And the Americans were keen to have NATO on board, and we brought individual specializations. Mine was data analysis on the testing that was going on and the user equipment. There was a memorandum of understanding between various nations and the United States, and these countries then provided people for the NATO team. There was also an Australian on there as well. It's not showing because, of course, Australia isn't part of NATO, but he was fully integrated into the gang. And in fact, the team wasn't just a decoration at the JPO. We were actually fully integrated into the whole fabric of what was going on. And we were treated like engineers alongside the United States Air Force people, Aerospace Corporation, who were sort of our technical mentors on top of all that. And then the various US government departments had representatives in the JPO as well. For instance, the Coast Guards were in there. We had the mapping agency, the Defence Mapping Agency, as they were known in those days. So the department was an eclectic mix of people who could contribute the bits and pieces, including the hard-nosed rocketeers who were busy pulling together the machinery to get these things into orbit. It's worth saying at this stage again, before I talk about the team, that initially the satellites were going to go out on the shuttle. You might recall that I think it was in 1986, perhaps, that the shuttle accident took place, and very quickly the Pentagon decided that no more military payloads would go up on the shuttle, and so it was decided to go expendable. The cost, which was worked out very quickly, was declared to be an extra $2.5 billion US, at which the Colonel said, "Oh, he said, I thought it was going to be a lot of money. We'll go ahead with that then." So the US Department of Defense has extremely deep pockets, which is really useful when you've got a program of this size and complexity. But when things do go wrong, they can react very quickly indeed. Well, this is the NATO team. Over the years, we had Wing Commander Hugh Corriat and Commander Alan Burgess, who were the NATO deputy program managers once in a while, and the rest of the time for the deputy program manager was either a German, a Canadian, and people from other countries. But the UK guys are all down on this, and you can see that I'm there 1984 to 87, and that's me standing on the CV-64 USS Constellation with Lieutenant Chris Brahaney, and we were sailing on the Constellation, picking up data from at that time, 2 sets of equipment, one manufactured by Magnavox, one manufactured by Collins, And it was a massive competition. Winner takes all was going to provide the receivers for the US Department of Defense. So obviously everybody was very interested in how well these systems were actually performing. This is a snapshot of the NATO team in 1984. In fact, it's our Christmas card from 1984. You can see me there in the middle with the Australian standing next to me in the light blue uniform. And we've got the Germans, Canadian, Dutchman, Italian, Dane, and Norwegian. And as the note says there, the civilian Danish guy, Peter Krag, as I said, a civilian, but kept turning up in a naval uniform, which used to surprise a lot of people. But that was Peter Krag. Yeah. Okay, next one.
April Fool's Day.
One of the things that is worth sort of accounting is that it wasn't all hard work. But it was April Fool's Day when, I'll just go back one slide, you can see that we've got a guy in the team, John Cardale, Lieutenant Commander John Cardale in 1976, as he introduced UK humour. It was April Fool's Day, and he was testing out in the ocean, and he sent a message back to the Joint Programme Office. Bad news and good news. The bad news is that the receiver's fallen over the side of the boat. And the good news is that it's still working at about 30 meters depth. It was a 100% April Fool joke. Unfortunately, the Americans were not quite tuned into the idea of April Fool. And the Joint Programme Office went completely berserk. He was recalled. By the time he got back, the word had got up to the 3-star general. He was dragged in front of the 3-star general, who said, "Is this the way that the Royal Navy behaved?" He said, "Well, actually, yes, it is." And the 3-star general was completely nonplussed at that. He said, "Oh, all right." And John Cardale left. It was quite a famous event that took place. Ah, dear, right, okay. This is the NATO Steering Committee. The NATO nations got together every year to discuss where the GPS program was going and how they would interact with it. And it was a bit of a travelling roadshow. In the time I was there, we met up in Italy, and then we met up in France. And you can see Nicholas de Chazelle standing in the front in the light-coloured suit in the centre, with Colonel Gaylord Green standing next to him, one of the most intelligent people I've ever met. And Ernst Willett, the NATO Deputy Programme Manager, standing next to him. These were quite high-powered meetings where a lot of the progress was really thrashed out, and the plans about what NATO en masse was going to do in the future. And it was, they were really useful meetings where a lot of good work was actually carried out. On the visit to Italy, this is just a sort of by-the-by type photograph. We went down to Granada, the airfield, Francesco Baracca's old squadron, and we were treated like royalty and shown around their starfighters. And there's Colonel Wayne Jones halfway up the ladder. He was the GPS JPO director at the time. Wasn't all hard work, as I say. And this, a lot of the testing was done in Yuma. Yuma has a test centre in the middle of the desert, nestling at the edge of the Chocolate Mountains, as they're called. And the thing about it is, it's a heavily instrumented range. So we could fly F-16s, A-6s and stuff like that with kinetheodolites and radar trackers. So we could get down to the sort of metric accuracy that we needed to be able to pull out the errors of the navigation systems on the GPSs in those days. It was really, really hot down there as well, and quite dangerous if we had people up range with the kinetheodolites and a thunderstorm came through. You get flash floods. So it was quite a hostile environment in the desert. I once left a can of Diet 7-Up on the back seat of my hire car, which exploded in the middle of the day because of the heat inside the car. It's that sort of climate we were talking about. But the wonderful part about it was that we all stayed in this place, the Yuma Cabana, afterwards. And the great part about it was they actually had a heated swimming pool. So after a day in the desert, throwing yourself into a 100-degree swimming pool and just lying there with 10-cent beer in your hand was a great way to unwind at the end of the day. This is a shot from there's an annual event in Yuma. It was the GPS NATO pig roast, and they basically barbecued an entire pig down there, and everybody went down into the desert, and it was a great social event. The other thing was that this period where this photograph was taken must be about 86-ish. It was the period when Halley's Comet was visible in the sky. And of course, you know, the sky in the desert is so clear at night, it gave an amazing view. Okay, well, I'll hand over to Snowball to stay again.
As Lyn said, he was the officer out there from the UK in 1984, which was where he was when I first visited the GPS JPO. And I ended up as being the person that shut the NATO project down at the end of 1993. The points on this slide, I'm recapping from the speech that Colonel Nicholas de Chazelle, who featured earlier. He was still the chairman of the NATO GPS steering committee at that time. The achievements that the team had made. The drafting of NATO STANAG 4294 was a very important piece of work in that it bound the NATO nations in to using GPS, which was, if you like, one of the big goals that the US had at the start, because there are no other NATO-wide systems, and certainly weren't at that time. Everyone had a very large mishmash of radio navigation aids that they were using. The second part was making GPS more user-friendly for the user. Once the security algorithms were embedded in the receiver, once it was keyed, it was classified as secret, which made it very, very difficult. Not so bad on a ship or an aircraft, but for anything that was attempting to be man-portable was quite difficult. So the idea was to build security that would stop the key being accessible if a receiver was lost or stolen. This was a NATO initiative, but such a good one that the US took it over themselves and developed it. But it did actually open the door, and NATO nations could have built their own. But that would have been short-lived, as you'll see a bit later in the program, the seminar today. The next thing was the development of a precise time and time interval interface out of the receivers. It wasn't naturally there, but it was seen as time as a product from the receiver was as important as position was. And that ITD GPS 060 remains unchanged to this day. It was developed in the early days by the technical working group of the steering committee and by Aaron, and has remained as was ever since. The NATO Green Book, again, was filling a gap in the market. We didn't realise what market at the time, because we found out that a certain gentleman who did GPS seminars attached to the GPS ION conferences was selling it at $25 a copy. It now has NATO unclassified on it, but it moved to AMP2, or it did. The final 2 years of the project was a wind-up phase, really. The original MOU one had been for a 15-year period, because it was envisaged that the NATO team efforts would finish at the end of the development phase. So we were moving to an operational phase. We handed back responsibility to the NATO subgroup 4, which met in conjunction with the steering committee, and that was now going to be the place where everything to do with navigation systems met. It had previously had its own technical working group, but that was for inertials, but they were amalgamated with the technical working group from the steering committee to form working group 4, which included technical navigation issues. The MOU 3 was signed in 1993 in time for the operational phase of GPS, which was coming, because it got to its full operational constellation of 24 satellites in 1994. However, a full operational capability was not given at that time, because there needed to be an assessment done by the DoD before full operational capability. Next NATO MOU is in work, as they need a document now more suited to the MCODO.
Right, going back to the early technical developments that were made at Farnborough. Following the visit to the US, the two lines of development were done. First, the Space Department began to look at the modelling of the orbits. Space Department had a close relationship with the Aerospace Corporation in the US, who were the main technical inputs to the JPO in those days, to refine the orbit prediction models using the NTS2 data. Remember, UK had a ground site for NTS2, so we had readily access to the data. And then by 1978, it was concluded that you needed only 13 parameters to define the ephemeris of the satellite, and advise the US accordingly. In RadNav department, Sudworth and Kilbington designed and built in the early 1980s a single channel GPS receiver. Here it is mounted on the 111 aircraft. The box in front is a Digital Equipment Corporation PDP-11 computer. That had about a MIP of processing capacity. Let me do a comparison. Your phone has got several hundred MIPS of capacity in it, so you can see where the limitation was in these days, and it's a big box. We flew that receiver at the Yuma Ranges out in Arizona, as Lyn described, in February 1980, and with good satellite positioning, which was rare in those days, they achieved a fantastic accuracy down to a couple of meters, but as I say, only for a few seconds. And that aircraft also contained a Ferranti-Fin 1010 inertial navigation system that was supposed to improve the navigation accuracy, but knowing what a Fin 1010 did in those days, it was probably a bit worse. One of the notable things is John Kilbington's patent for a fast Fourier transform correlator, which was way ahead of its time in July of 1986. Again, as I said, we didn't really have the computing capability to do that sort of work real time in those days. The work continued in the Space Department. As Lyn said, the original plan was to launch the satellites by shuttle, but however, that was not going to be the case, and they had to be realigned for the Atlas F and Delta rockets. And Space Department did a complete replenishment analysis based on that strategy by May 1978, which was, I think, one of the great underestimated pieces of work. Again, the navigation analysis of the NTS-2 tracking data, October 1979, was ahead of some of this work actually being done in the US at that time. And accuracy prediction based on some of the orbit models that King Healy had developed, and the K of loss of what would happen if the ground segment was lost. And again, another assessment of the vulnerabilities of the satellites to a direct attack. So UK had done a fairly comprehensive piece of work into some of the problems that GPS was going to face in the forthcoming decade. The work with receivers continued. The RE-111 went back to UMA in November 1980, and more successful that time. They were getting consistent accuracies of 20 to 30 meters, which compared to other systems at the time was a fantastic accuracy on a relatively high dynamic platform. On returning to the UK, it was realised that REE were not going to be able to build a full receiver and turn to UK industry. Contract was awarded to SDL at Harlow for a feasibility study, and then for the development of a full receiver, which was delivered in late 1981. And here we can see the receiver. It was 5 boxes in all. It was installed on the left in a Wessex helicopter and in a Land Rover. Probably the only thing recognisable these days is the Land Rover. You can see it filled up the majority of the back of the vehicle. But it was the first installation in the UK, and probably one of the few installations outside the US of a mobile receiver for land vehicles. We had realised at the very early stage that GPS was vulnerable to jamming, and the Areans Research Group was brought in to look at the development of basically to take radar adaptive antenna techniques and apply that to the GPS system. And that means that the way the system works is that to try and you need to wanted signals are from the GPS satellites, and the unwanted signals are from the jammers. So you form deep nulls in the radiation pattern towards the unwanted signals. And that is achieved by what's called control a phase array, and by controlling the phases of the signals from that antenna array. SDL were awarded a contract and investigated various methods and decided that the correlation loop was the most attractive way forward. Direct matrix inversion wasn't possible. We didn't have the computing power, and the weight perturbation algorithms increased the noise figure, which was in a GPS system was always not the thing you wanted. So the correlation processor for vector weighting networks was developed in a feasibility study, and then a demonstrator system which was delivered in the early 1980s. It consisted of a 6 antenna array shown here on the left, and you can see the 2 boxes, and that was mounted on the 111 aircraft and flown at UMA in 1984. The antennas were actually made at Farnborough by Dave Hazel in Mike Sidford's group. There was one on each side of the aircraft in those days. REE had its own flight certification for experimental equipment, so we could do everything in-house, as it were, which was a great advantage in getting it done on time. But coming up to the late 1970s, there was trouble in Congress. The bills, as Lyn said, change over from the shuttle launches to rocket launches were causing budgetary problems, and the FAA were beginning to become interested in the system because they were running a whole suite of ground radio navigation aids, and Congress were pointing out, or the General Accounting Office were pointing out to Congress that you've got duopoly going on here, and who was going to run what. And the recommendations were that DoD would be confined to basically three systems: a GPS, an inertial, and a Doppler nav system. And the size of the constellation was pruned from 24 satellites to 18. And the FAA was told to improve its evaluation of Navstar and the benefits to civil aviation. In the UK, the affordability of the 5-channel equipment we had developed was becoming a major problem. It was analog, it was very labor intensive to manufacture. And for a time, we looked at the use of a single channel sequential receiver that hopped between satellites. The problem with that is it really didn't handle the dynamic conditions very well. But then came the digital revolution in the 1980s. And this led up to what was called the Phase 3 GPS test program. So in the mid-1980s, Plessey Avionics came in and began to develop a GPS receiver, a digital receiver. They did anti-jamming systems from Rogue Manor Research, and from RE put in some funding money, and the Admiralty Compass Observatory at Slough were becoming interested in receiver designs for ships, and put in some research funding from them. The whole thing was demonstrated by a program like testing at Yuma in 1989. RE continued to fund the SDL on their receiver, and they developed similar 5-channel receivers with antenna arrays. This is the first flight of the SDL 2510 receiver in very early 1989. I think this was just before we went to Yuma, and you can see the aircraft starting up and taxiing out. Then on the what was called the arrestor runway at Farnborough, because it was used to trial the aircraft arresting systems, and then down the main runway to take off, going to the southwest. The international test program for the Phase 3 GPS equipment, the US encouraged the UK to take part in this program, mainly because of our work with the digital receivers and the digital antenna control systems. And the US lent us some Rockwell Collins 3A receivers, which Rockwell had then won the production contract for the US Air Force, and they, with a US AE-1, which was made by E-Systems in the US, which was their anti-jamming systems. We flew them alongside the SDC and Plessey receiver and anti-jamming systems. In January '89, we took the 111 to Yuma, where we flew 20 sorties in all, 6 navigation sorties and 14 jamming sorties, with up to 6 jammers on the ground. So it was a very intense jamming environment. By that time, the GPS constellations gave us about a 5-hour window over Yuma with a good PDOP. PDOP is the precision dilution of precision. It basically means that you need a very low PDOP for a good navigation solution. And it's terminology which, if you multiply the range error by the PDOP, then you roughly get the navigation performance. So a 3 to 4 PDOP means a navigation performance of roughly about 12 meters in those days. The aircraft was fitted with dual systems, so we could fly 2 systems side by side at the same time. These are the anti-jamming antenna arrays, they're 7-element arrays mounted on top of the 111. And we flew basically with either 2 US arrays, or with a US and a UK, or 2 UK's arrays on this hatch to test the systems. The systems were the SDC receiver, which was a very small, thin digital receiver, 5 channels, with the 7-element AJ system, and you can see here mounted on the side of the aircraft. The Plessy had a similar system, that their receiver was slightly different size and shape, and their AJ system hadn't quite reached the maturity of the SDC systems. And this was a prototype system developed by Remote Manor Research, which was Plessy's research establishment in those days. Here's a Rockwell. This was a standard US Air Force Rockwell RCVR-3A, generally known as the 3A, which was flown on our aircraft. We had a Lytton LN-72 inertial loaned by the US to run that system. Again, we installed 2 of these systems on board, so we compared the performance of one system linked with the US AJ system and another system linked with the UK SDR 2515. The 3A receiver was an IF, but there was a separate RF to IF conversion box. So SDC actually made a IF interim frequency version of their box to actually work with the Rockwell receiver. We had another receiver on board, which was made by Polytechnics Electronics, which was a company up in Daventry. Polytechnic were known for the maritime market. If you were an affluent sailor in those days, you would have bought yourself a maritime transit receiver. In the late 1980s, it renamed itself Navstar because it realised nobody else had patented the name in the UK, or Bridges had the name in the UK. So it became Navstar in Company's House. The XR3 was really developed for the military and surveying market, so it didn't work terribly well on a BAC 111 that was being enthusiastically thrown around the skies. But it was interesting that had a long history, and the engineers from Navstar designed Intel's GPS receiver devices that you will find in your mobile phones and computers until 2020. The bottom picture is of a further development, the XR4, shown on a Comet navigation station. Anything to help nav in those days. It was a very early product available in the early 1990s. This was a bit of kit made by STL. It was a data acquisition unit. We couldn't have flown the Yuma trials without it, because this collected all the data from the equipment on the aircraft, and that data was then translated into a Yuma format and processed by Yuma overnight. So we had it for the next trials range. This is the team at Yuma from REE, you've got STC, Plessy, and various American gentlemen in there. The human results, basically, it proved how good the UK anti-jamming systems were, and that we had something really to offer the US. In the early 1990s, UK industry was changing. STC sold their GPS business to COSA, who were then part of Raytheon. They've since changed their name to Raytheon Systems Limited. Plessy were taken over by GEC Marconi, and Rogue Manor was sold off to GEC Siemens, and then to Siemens, and then acquired by Plessy in 2010. The US were in denial, however, of really how vulnerable the system was to interference and jamming. We found that a CA code receiver could be jammed very quickly, but at a power level of -130 dBW, and that is at a -130 dBW is really equivalent to a 1 watt transmitted power at a 50-kilometer range. The comparison with some of the work then being done for the instrument landing system and VHF interference from adjacent communication system was a prediction of the problem with GPS. And then a very unfortunate thing happened. The Korean airliner 007, nothing to do with James Bond, we're told, strayed into Soviet airspace on a flight from Ankara down to Korea, and the Soviets shut it down. That led to the Ronald Reagan authorizing GPS for civil applications. This was backed up by Congress, again being very wary of the cost of the GPS system, and the instruction to the FAA to take the system to ICAO, which it did at the ComOps meeting in 1993 to make it a formal ICAO system. In fact, the ComOps meeting, they tried to make it the sole system for aviation. Here we are 30 years later, and they're just getting it to a point where it's becoming operationally acceptable, but still with all the current radio navigation ground aids. That meant that to make it acceptable for civil operations, the selective availability was becoming obsolete due to the number of differential services. And what's the point of spending money on a differential service and on the selective availability? And in May 2000, Bill Clinton, president, ordered it to be removed. And as far as we know, it is not being reinstalled on current GPS satellites. Into service in the UK, but this is the GC Marconi became outfit QIF, which was fitted to all the Royal Navy ships. The SDC product was engineered by Kelvin Hughes and sold to the Royal Australian Navy. In 1994, a installation was done for the Hercules 130C upgrade, and later the 130Js, and that was a full STC 5-channel receiver with a antenna, a control unit, an AJ system, so a full 7-element antenna. And that was linked to the aircraft inertial navigation system. A similar system without the AJ was fitted to the Nimrod MK Mark IIs. A little later, the GC Plessy system was fitted to the Tornado GR4 and several other UK platforms. Along with these development of those systems for aviation, we needed an in-house test facility because the cost of flying the stuff was becoming prohibitively expensive. And STC had developed a simulation box, which was then taken up by the STC test equipment group at Peyton. Maurice Bard was the project manager, and they delivered us the first constellation simulation in 1994 at Farnborough. That system is now manufactured by Spirit, who have a large proportion of the professional simulation market. The SDR then 2420s that were fitted to the Hercules were submitted to the GPS JPO as technical demonstrators for what was to become their GPS antenna system -1 program, which was their AJ program, and that won the competition. Was adopted by the DoD in 1977 as the US Air Force standard AJ system. Other things we did were we tried GPS in shells. This is just one of the examples, and we did actually fire it, and it worked. We were able to acquire it in flight, and it did roughly hit the target we wanted it to hit. Further developments were going on at Roke into AJ systems, again with the digital architectures becoming available, then direct solutions to replace the correlation detection program were being developed. Roke were developing custom ASICs for the very high performance of digital anti-jam systems, and incorporating them into what became what was the Advanced Digital Antenna Control Unit, a 7-element system. And again, the US became very interested, and we loaned them a couple of systems. The other problem was the power. These systems were okay in aircraft, were very power hungry, but for land vehicles, they were more of a problem. So in around about 2010, we developed a very low power, low latency anti-jam electronic system going back to the antenna and analog days, and a few thousand of them were deployed in active service for Afghanistan to protect the comms, the timing system in comms. And if you remember Alan Noble's brief about the development of the timing ICD, this was all part of that work. Then Roke developed the Land Shield, which was development of ADAP, which was a small 4-element system, again made by Raytheon, and introduced that into the first true anti-spoofing technology for surface, so that they could spot if the system was trying to be spoofed by that system. The picture of the ADACU, it was a big box, and that was we contracted Trimble to get them to make a digital receiver for us, briefing the CNC strike to John Allison of all this work on this simulator at Farnborough. And then there was another war in the 1990s. The US really woke up about the anti-jamming problems, and unfortunately this led to the end of the UK receiver development. The introduction by the US of a device called the Selective Availability Spoofing Module, which included all cryptographic components, basically meant that there were no separate components to buy. You can only buy a SASM. SASMs were US only products. So that really was the end of the UK receiver developments. But however, we continued with the AJ systems. In 2002, Defence Procurement Agency issued a requirement for, under the NAVWAR programme, for a multi-beam former, multi-beam steering, space-time, space frequency adaptive processor, enabled broadband cancellations, direction finding of the jammer, and 2 systems were developed. This was the common 4-element box, where they also made an 11-element box, and Raytheon continued with their 7-element system. The 7-element system became the digital antenna control unit, which won the US Navy's program in the early 2000s for their anti-jam system. I had to include somewhere a bit of electronic architecture to show them some of the complexities of what we were up with, and so that's the advanced digital antenna control unit. It includes a digital receiver module, which is the small box at the bottom right-hand corner. By that time, the electronics had been shrunk, so the digital unit, which you saw in the big box, was now shrunk to the same size as the gas one, and that there is a 4-element land shield system alongside it, just as comparison. That's got the antennas and the electronics in the same box. The box on the left requires a separate antenna control unit, or separate antenna array. Some of the platforms that ADAP have now been fitted onto, quite an array across NATO. Raytheon released a press release in September 2021 on their 15,000th delivery of Gas 1 and ADAPs. They have currently an extant contract from the UK Defence Logistics Agency, and they have supplied even UK Ministry of Defence with its 1000th land shield unit. But that was the location device, so you could locate the jammers, and a little video camera antenna screen, so you could point it, and where you got the maximum power, you could chase it into where the jammer was. We had a look at antenna anti-jamming systems for a soldier, putting it on the helmet. That was a very interesting piece of work. I can't remember the name of the gentleman on the right that's currently holding a handheld receiver, and the wire, the electronics, but it worked. We were able to demonstrate the system. Then came the requirement, as GPS was being integrated in various systems, there was a major problem in testing a GPS integrated with an inertial, because the only way to make the inertial work was to fly it around, which, as we said, was expensive. So an open system architecture, STANAG 4572, was developed that simulated alongside the GPS simulator, using the same dynamics modeling system that drove the GPS RF to drive an inertial error model, which then the output looked like an inertial system, which the integrated system could then use to test its Kalman filter integration and identify the errors that were going on in the inertial. So if the system on the right there, which was the GPS inertial integration algorithms, gave you the same results as the errors you put into your inertial system, you know you were on the same wavelength. And that was a highly collaborative program between the DSDL, the GPS Wing, Aerospace Corporation, Wright-Patterson Air Force Base, and Spirit, the receiver simulator manufacturers. We went on in the NAVWAR program. Again, flying aircraft was expensive, so we developed a chamber at Boscombe, an anechoic chamber that had the satellites in the roof, So you could simulate where the satellites were coming from to test AJ systems with jammers around the side of the chamber. That's being further developed at the moment such that the whole thing can simulate the dynamic platforms. Going back, the digital AJ systems were big, heavy, well, big, power heavy, power hungry. So we wanted a system that was applicable to small, low cost, potentially land vehicles. We tried it as it's just on soldier's helmet. But we needed a low cost, low power system. And we went back to analog technology, developed a RF small integration chip. You can see the one at the top left hand corner is 4-element system. And the antenna is shown, that cone device in the middle. And that was made by Raytheon again under various names: mini gas, gin can, RCAS, microgas. But over 1,000 of those were made to protect the comm systems in Afghanistan. And a postscript. This is the agreement between the US GPS and the EU Galileo working group on signals, which was conducted. Professor Gunther Heim, Munich on the right, hosted the meeting, and this is the celebration glass of champagne at the end of the meeting. Thank you very much for your attention. I'll hand you back to Hannah.
That's brilliant. Thanks so much. So we've got a bit of time left now for some questions. So just drop any questions that you got in the bottom of the screen, sort of Q&A section, and we'll get through to them as many as we can. So we've got a couple already. So the first question is, how many people were working on the GPS MOD programs in the UK at the peak? So start with an easy one.
MOD people. By the time we were DERA, which was the late 1990s, I was running a team of 40, plus Rob's team in Abbey Wood.
A lot.
And then there were the commercial companies who were doing all sorts of bits and pieces.
In the early days with Plessy, there was an engineering team of probably about 12. But the STC team, which had been working right from the beginning, as we saw there, was very large, led originally by Peter Blair, and then at the time I was there, Ian Vance, Rob Hall, Peter Jones, and Philip Hargrave were the people I interfaced with. There was probably a team there of a good 20 plus out of the research establishment, and then that changed when we set up a company, STC Navigation, and again that started to become development for production, and that was again upwards of 20 people in the system.
And I guess, I mean, I used to work at Spirent, and I came in after 2000, but the simulated team at Spirent in the late 90s was probably another 10 or 20 people, something like that. And by the way, I exchanged LinkedIn with Morris Spard the other day. He's still very well.
So we got a comment from Terry Moore on that. There may have been a few academics involved in GPS in UK universities.
One or two.
Sorry.
And then, I feel a bit cheeky and ask my own question. So I don't come from a GPS background at all, so do forgive the spits and invested. But I was wondering, did you have any sort of concepts of how ubiquitous GPS is going to become when it first started? I mean, now we're all carrying it around in a phone. Everyone's got one. I think there's more GPS receivers than there are people.
There was some reluctance, in fact. I remember when I was working in the JPO, we had to go around to the various US military organizations to say we're going to use one of your bits of equipment, one of your airplanes or something, because we've got this new system coming along and we've got a letter from the Pentagon that says we can do it. And with the B-52 bomber, for instance, they said, well, what does it do? And we said, well, it'll make your bombing more accurate. Because with a strategic aircraft, get out of it. And they just wouldn't believe that it would do it. We tried to put we took the equipment to the CV-64, the Constellation, 2 sets, Collins and a Magnavox set. And again, when we arrived with it, they looked at us and they said, well, what do you want to do with it? And we said, well, it's navigation equipment. We're perfectly capable of navigating this aircraft carrier, thank you very much. And who the heck are you? And so we were given a little cubbyhole in the back of the bridge area. We put some equipment and the data recording there. We carried out the trials over a few months. We went down to San Diego to collect the equipment. And at the bottom of the gangplank, admirals, compliments, you're not allowed on board. And they sailed with our equipment because it was so good. They wouldn't give it to us back. So, there was a reluctance in the beginning because people just didn't believe it. It was just so accurate. But they once they got used to it, then the acceptance was very, very quick indeed.
So it's actually shown it first.
Because nobody saw the development of microelectronics.
Oh, okay.
Development of microelectronics.
Yeah.
Because you saw the size of the original receivers, there were boxes, they took many tens of watts to run. So your phone working on a microwatt and doing the same thing is where it's why it's taken off.
And I guess cheaper as well because it's all. Thank you. I guess we've got one now from Catherine Mitchell. Does anyone know how the GPS radio frequencies were selected? My undergraduate students were asking me, and I was not sure of the exact reason for the final choice.
Well, basically, the International Telecommunications Union dictates radio bands for various applications. So you can't just choose any frequency you like. There are specific bands for applications, and one of them is space transmissions to Earth. And GPS L1 is in a protected band. L2 is not in a protected band, it's co-primary with long-range radars, if you like.
It's worth having a look at atmospheric absorption as well, because that will help you to see where the windows of opportunity are if you want to transmit a very low power signal at great distance, which is the sort of situation you find yourself with GPS.
The 1 to 1.5 megahertz band is optimum in terms of the wavelength. As Rob says, in terms of the transmission to the ionosphere, you don't want to go down frequency into the VHF bands, and when you go up in frequency, your antenna losses become at the receiver become very high. So that was the optimum band, and as Alan says, fortunately they found some areas that nobody else was using at the time, because we're going back to the early 1970s. I mean, the spectrum wasn't as crowded then as it is now.
And actually, there's a little clarification on, or extra bit of information from Terry Moore. The frequencies are integer multiples of the basic 10.23 megahertz.
Yes,
Everything is a multiple.
Everything.
2-3 megahertz.
And I think one thing I can add, not specifically on the frequencies, but just on the whole system design in terms of, the orbital height and the frequencies and some of the signal parameters. My understanding is they were really thrashed out and decisions were made, correct me if I'm wrong, Jess, at the Lonely Halls meeting. I mean, there was a lot of information on the table, but I think I might be wrong there. I'm getting some shakes in the head.
No, I think aerospace had already solved those problems in the transition and the 6 to 221B. So I think that wasn't really an issue in the Lonely Hawk. It was more the architecture of the system. Were they going to fly high-grade atomic clocks was one of the big issues. Orbit parameters possibly, orbit heights, because GPS is in a synchronous 24-hour, 12-hour orbit with the Earth, so it has some pros and cons.
Okay, thank you.
Thanks. So another question, any comments on why UK MOD stopped having a representative embedded within the GPS program office in Los Angeles? Has that made collaboration harder? That was a very pointed look there.
I guess I'd better take that one. The answer is largely to do with the cost of having somebody out there. Unfortunately, they're usually serving officers. These things are relatively rare. Their rates are expensive. They were staying in a relatively attractive part of the US, which doesn't come cheap. And so at the end of the day, unfortunately, it's financial pressure, which, having said that, there are international agreements with the US that are still ongoing regarding GPS and navigation warfare. And these things give us the opportunity to have an embed out there in the US, whether it would be with the GPS wing or GPS directorate, as it is now called. That may be the case. It might be in another facility elsewhere in the US. The opportunity is there. Sadly, there aren't that many dollars around within our pot, and we just have to prioritize.
Another question, how do you see LEO constellations fitting into a system of systems approach to address GNSS's vulnerability for civilian application?
How long have you got?
Should have that on the last.
The main thing is they cannot transmit on the same frequency. They've got to be on a different frequency. So, and why, and the other problem you've got is that GPS is free. You don't hear too many complaints about it. Your mobile phone continues to work. Okay, you may get a bit of interference from something for the system we use, but who's going to pay for the alternative systems? Unless you're getting something else. So if you're hanging on the back of a comm system and you're providing a timing satellite position information on that comm system, then it may work. But how are you going to get the LEO, the position of the LEO satellite to the accuracy you require? Well, maybe the LEO's got a GPS receiver on it.
One of the problems with a LEO satellite is that, I mean, they're low down by definition. And so the time it takes to traverse your field of view in the sky is very short compared to the hours that you get from the MEO side. The orbits are going to be a bit more lumpy as you get closer to the Earth. So that means the ephemeral data is going to have to be updated very regularly.
Well, in fact, transit is a LEO system.
Yes, transit was at 1,000 kilometers, they're about polar orbits. But if you're going to be down at low Earth orbit, trying to emulate the GPS approach navigation, you'd be swapping your ephemeral data every 6 or 7 minutes, you know, so the receivers wouldn't have time to navigate. It's I can understand why people have thought about this idea, but the MEO orbit was chosen for very good reasons, because it gives you so many advantages of putting something like GPS together. And once you come down into the lower orbits, it just becomes a nightmare. And one of the beauties of the systems that we have at the moment, GPS and GLONASS, etc., they're all on the same frequency, so you can use the same circuitry in the receivers. They've all got the same Dopplers. If you've got a LEO satellite transmitting into the same system, the Dopplers are too high, they can't track them. There are so many reasons why LEO ain't a good idea. Let's leave it at that.
Why offer something if it's free? That's the thing. They'll be able to get some benefits from LEO systems if they're up there for other purposes. If you're going to start afresh and design a navigation system purely on LEO satellites, there are lots of things you need to consider. Where are you going to put your ground control system? You need all of the monitoring stations, so many more, because you need to keep the information fresh in those satellites because they're traveling so fast and going overhead so quickly that, you know, they're also suffering from, you know, orbital perturbations more severely at that sort of altitude. There's a whole range of things you need to think about. And I guess it's probably worth reflecting. The US have had to spend an enormous amount of money on making certain that their ground control segment is absolutely rock solid from the cyber perspective. So you have to begin to ask the question, who is going to be prepared to invest that amount of money in what might be a commercial system for LEO to provide you with, you know, bulletproof cyber dimensions for the entire constellation? Security is absolutely everything for the military. Now, for commercial purposes, that might not be quite the same.
However, resilience is the hot topic at the moment, and receivers tend to be at their most vulnerable when they're in acquisition. As Lyn was saying, you're going to be swapping your satellites very, very often, so your receiver is going to be vulnerable.
There are some things you can do with low Earth orbit satellites. There's a lot of work going on time transfer using low Earth orbit satellites. As John said, time from GPS is one of those things that wasn't originally envisaged to be important, but of course it is very, very important. Really accurate time for things like algorithmic trading, you know, within milliseconds and stuff like that. Now, if you want to have your own atomic clock and keep it synchronized with somebody, it's possible using techniques with low Earth orbit satellites, but not as a navigation system that's as robust as GPS or GLONASS or something like that.
It's horses for horses, and it'll be a mix at the end of the day.
Orbits are chosen very, very carefully for the payload that's working. That's why nobody else is bothered going down to the low Earth orbit.
Well, it's interesting, low Earth orbit's becoming very, very crowded. When you've got people putting up thousands of low Earth orbit satellites for comms, you might be able to hang a nav system on the back of those, but be very careful of the being able to pick up the debris after the inevitable collision.
I'm in that. So we've got a couple more minutes left for us, so 2 more questions maybe. So put them in if you've got any. And now we're going to take it back to the US-UK relationship. Were there also the visibility from the US program team to the UK over the time? Like, what was the visibility like between the 2 teams? Were you sharing everything?
Sorry?
No Americans coming over here.
No, we didn't have there. It wasn't an exchange program.
Okay, brilliant. And
With the more modern MOUs, and I'm talking in the last 10 years or so up until the present day, the US are always very, very interested in having joint cooperative programs, and they would much rather get into a situation under MOUs where nation X is bringing certain technology and they bring certain technology. You join the 2 together and improve the overall system. So that is something that is always attractive to the US, and UK anti-jam systems and American military GPS receivers are absolutely classic of that style of approach.
and then a final question. Were the anti-jam antennas export controlled items from the start?
Oh yes, absolutely.
So dual use technology under the Bassenheim agreement.
Okay.
But we make them in the UK, so we aren't exporting them if we want to use it on our critical national infrastructure.
Okay. So I think that's everything. Any further comments that anyone would like to say? So we close up.
Well, thanks for all the work putting the presentations together. I learned a lot.
Yeah, that was brilliant. Thank you. And we start to host it on the Virtual Museum. It will be a brilliant process. So thank you so much for all the work you put in as well. I hope it was interesting, reflecting as well. Thank you. And thank you everyone for joining. If you have any other questions afterwards, please do get in touch with me. So I'm hannah.sherrod@ring.org.uk and I can pass on any questions to the speakers. So thanks for joining. Hope to see you again at another Ring webinar soon. Thanks everyone.